So I promised to talk about Lagrange multipliers with multiple constraints.
To break a promise.
And then to send you on your turkey way, I will talk a little bit about the proof of Lagrange multipliers. So here's the basic setup. I might as well state the theorem for you. So, because I haven't really made anything explicit to this point. So we're studying a C1 function f on Rn, and we want to restrict it to some constraint set. So economists do this stuff all the time, physicists do this stuff even more often, and mathematicians as well. So you have a constraint set given by a function g that's giving you m constraints. And so we're going to look at the set of points where g is equal to some constant. Now that constant's a vector. So this is going to be our constraint set. It would be nice if that constraint set were a manifold. There's that word again. Do you remember hypotheses that would ensure that?
If the derivative was
No, if I have multiple constraints.
If the derivative of one of the g of x is like the things is never zero or not zero.
No, but you have a bunch of g's.
the composition of that.
No. Yeah. Has to do with the rank of the derivative being equal to the number of equations.
Okay.
So suppose the rank at some point, and that point is in your constraint set M. Assume the rank is M, then that means near A anyway, M is going to be a nice manifold. And I'm going to say, then, if A is a constrained critical point, so that means restricting your function f to your constraint set. A is a local max, local min critical point. Then the condition is going to be that the derivative of f, well, I'll say it in terms of gradients for you. The gradient of f at A is a linear combination of the gradients of the g's for some scalars lambda 1 to lambda m. So when we had just one constraint, when m was 1, we just said gradient of f is some scalar times gradient g. Now I'm saying that if you have more constraints, the condition is that the gradient of f be in the span of the gradients of the components of g. Okay? So I want to do a couple of examples and then I'll mumble about the proof. What is, by the way, just before I mumble, what does this condition translate to thinking about these vectors?
They're not
Non-zero.
zero.
Well, they're certainly not zero, but the rank is a much stronger condition than that.
Gives you a signal. Oh, linearly independent.
They're linearly dependent. So this rank condition is the condition that the row vectors of the matrix, which is the gradient vectors turned on their side, are all linearly independent. All right. room here. Glad to see stuff racing as usual. Indelible chalk wins again. Okay, so let's do, as a warm-up question, a question very similar to one of your homework problems. I'm going to change the numbers slightly, but this, you will remember a question like this. What are the highest and lowest points on the ellipse? Sounding familiar?
Yeah.
So let's take the ellipse that we get by taking the unit circle in the xy plane and making it into a cylinder, and then intersecting that cylinder with a plane.
That's not an ellipse
So I'll take some plane that may or may not be drawn to scale in this picture. If I take a plane, and let me just get the numbers the way I have them in my notes, x plus y plus 2z equals 2. So it's not quite what you had for homework, but it's not too far off. So when you take the plane that's on a bias relative to the cylinder, and you intersect it, you in fact do get an ellipse here. And I want to know what the highest and lowest points on that ellipse are. You guys did a problem like this for homework and discovered it was really a single variable calculus problem, but now I'm going to do it as a Lagrange multipliers problem. So what function do I want to maximize, minimize? I want to extremize
f of something.
f of x, y, z equals
C.
z. All right, highest and lowest, I, of course, refer to the vertical axis. We're going to talk about highest and lowest. Subject to constraints.
X plus y, or x squared plus y squared is 1, and no.
So I have two constraint equations, so I'm taking the function g that maps R3 to R2 now, and g gives me the constraint equations by sticking in my functions, x squared plus y squared, and x plus y plus 2z. If I set that equal to 1, 2, that's my constant, then that defines my ellipse. Got it? Yes, sir.
There's a problem kind of like this on the web work, and why can't you just solve for z in the constraint, in the one constraint to the right, and then put that in for z in the f? Because
Like you did for before?
yeah, for the load.
Yeah, so nothing stops you from doing this without Lagrange multipliers, but I want to warm up using Lagrange multipliers before we do a harder problem. Yeah, as I said, it's like a homework problem that you all did very easily. But all right, so what are we supposed to do? We're supposed to look at gradient of f. So what's the gradient of f? Is some constant times the gradient of the first constraint equation, function, plus some other constant. So rather than writing lambda 1 and lambda 2, I'll just write lambda mu if you'll allow me, gradient g2. So this is going to be lambda times, what's the gradient of the first component function? 2x, 2y. So I'm going to pull the 2 out just because I don't like 2's today. And then
You never liked 2's.
mu, the gradient of the second component function is 1, 1, 2. Okay, well now I have to deal with that too. So the question is, when is the vector 0, 0, 1 in the span of the two vectors x, y, 0 and 1, 1, 2?
This sounds like we have to just solve it. This is something we've done before.
So, I mean, yeah, so you can write this down in terms of column spaces and matrices and doing row operations and all sorts of stuff we did months ago, it seems, right? You're asking, if you took the matrix of these as columns, and you put that as your right-hand side, when would be consistent in your equation.
That's what I'm saying.
But we can just do this by thinking, can't we?
I don't want to think.
What has to be true about x and y? They have to be equal because they're supposed to cancel out the vector xy with a multiple of the vector 1, 1. Right? We're asking, when is xy plus some multiple of 1, 1 equal to 0? That's equivalent to saying, when is xy a multiple of 1, 1? So it has to be x equals y.
1 also has to equal 2 times some number.
Now, say what?
1 has to equal 2 times some number.
Oh yeah, 1 has to equal 2 times some number. How could that happen?
Fraction.
Seems like, so I was telling you guys when we had one constraint not to worry your little brains about lambda, but now we actually do sort of have to worry about what these coefficients might turn out to be. So mu has to be a half. Does that tell me something further?
That those are 1/2. I'm not being very articulate.
That
The other ones,
So if mu is a half,
2 lambda x and 2 lambda y equal 1
well then, basically
Oh, wait,
2
no.
lambda x
Yeah.
equals 1/2,
negative 1.
and 2 lambda y equals 1/2.
2 lambda
Negative
x.
1/2.
2 lambda x equals x.
A negative 1/2. This kid's.
No, negative 1/2.
Mu? Oh, this is wait. Oh wait, that's not true.
so do we know anything about x and y yet?
They're equal.
I mean, you only have, right, we have that they're equal, but this condition is not telling you anything further about x and y because of the lambda, right?
Yeah.
So I don't, so even though Dan was prattling on about equations with you putting a mu equal a half here and trying to say what that said, it still gives you x and y's relating to lambda. It didn't help. So let's see where we get just from saying x equals y. Now we have constraint equations, do we not?
Sure.
So if x equals y, that's going to end up telling us that there's only 2 possible points on the circle. Where x squared plus y squared is 1. So we're going to have, this tells us that xy has to be plus or minus 1 over root 2, 1 over root 2. It's either this point or it's that point. And I'm done.
Those are
This,
2
this,
points.
this is a purple herring. It doesn't help us.
But it's interesting.
Well, purple herrings often are interesting.
What do lambda and that other symbol actually mean then?
So I promised you in the single variable condition that there was an interpretation of Lagrange multiplier which will show up in challenge problems. They don't particularly have meaning, other than saying what linear combination gives you the vectors. I don't have a physical or geometric meaning for them. So I'm going to say, though, that this condition was irrelevant, and knowing x and y, then my second constraint equation tells me the z's. So I'm done. All right, my function, I just get by sticking in this x and y and saying, well, what's z equal to? So I'm going to have f of 1 over root 2, 1 over root 2, whatever the z is, equals whatever the z is. Well, what's the z?
1
2
minus 1
minus 2, or plus or minus 2.
Right? X and y are both 1 over root 2, so I have 2 over root 2, which is approximately root 2. And so z is going to be 2 minus root 2.
Wait, but it's divided by 2.
Oh,
It's
but
2z.
Yeah, it's 1.
Oh yeah, it's 1/2, thank you.
So it's just 1.
Thank you. So it's 1 minus 1 over root 2, actually. Okay. Anyway, it's 1 minus 1 over root 2. That's the high value.
No, the
That's
low value. right? Because the other one will be 1 plus 1 over root 2.
Yeah.
Yeah, you're right. Because when I put the negatives in,
But they add to the other side.
negative, negative, and then the z value would be 1 plus 1 over root 2, right? Thank you for correcting me. Yep. Okay. So that was sort of disappointing. I mean, that was really a letdown that these equations I didn't use really anything except this one fact. So let's try it with a slightly more interesting version. Let's try instead a paraboloid.
What's probably gonna happen?
Change the second constraint to the equation z equals x squared plus y squared. So now, again, the calculus is done once I write down the gradient vectors, and then it's just a matter of doing algebra correctly. So now I still want to do 0, 0, 1 as a combination of x, y, 0 with now the vector. Okay, so I have to rewrite my second function here as what? How about I do
X squared.
negative x squared minus y squared plus z equals 0. So I'll have negative 2x, negative 2y, 1. You okay? What's the question?
No, it doesn't be changed.
I'm just changing the second constraint equation, so I still have the cylinder.
Wait, the second. So x squared plus y squared still equals 1 as in the first equation?
Yes. I still have the, oh, that is not what I wanted.
Yeah.
Change
like,
the,
what?
yeah, change the first constraint.
No, I meant to
Because
change the
then z
first
equals 1
constraint.
the whole time, and it's just like...
Yeah. That was dumb. Thank you for,
Sorry.
no. I was about to figure it out for myself. But,
I just like to ruin half of people.
all right, so now we have the paraboloid instead of the cylinder, and we still have our green plane. And interestingly, you might wonder, is the intersection still an ellipse or not?
Yes.
Well,
Looks
it's
like
not
it.
gonna not be an
It is in the Wait,
It's
Because
not going to follow from,
They stretch it. Is it gonna go like up and down, so it's gonna be an ellipse, but it's not flat? Or is it?
no,
it
it's
is
in the
gonna
plane
it'll be
still.
flat.
it's gonna be an ellipse because it has two, if you
It
put...
certainly doesn't fit the classical description in terms of slicing cones or slicing cylinders.
But if you put z into the other equation, like if you solve for z for g1, it's like x squared plus y squared, which is still like,
So that's telling you the projection into the xy plane
yeah, but it's still like an x squared
Is-
plus y squared term.
is quadratic.
Yeah.
And then, in fact, it does still have to be given by a quadratic equation in this tilted plane. You'll learn how to do that in the last chapter of the book. And it clearly is not going to be a hyperbola or a parabola because it's going to be a compact set. But if you tilted the plane enough, that wouldn't be true. So it really depends on how the plane's tilted.
Oh, yeah, that's interesting.
Okay, so let's see. So taking the gradient of this guy, it's negative 2x, negative 2y, 1, multiplied by lambda, and then we have mu times 1, 1, 2 as before. Right? Yeah. Now this gets slightly more interesting.
Wait, why are we
Now I don't got no 0,
Where's the zero?
and I didn't even give myself the answer in my notes, so you're going to have to help me do it. So what do we deduce still?
mu
How does
equals
Why
how do
half
we
of
get the 0 here?
X equals Y.
Still, x and y have to be equal because having 0 here tells us that the first two coordinates here give a vector that's parallel to 1, 1.
and
So we still have x equals y because the vector xy is some scalar multiple of 1, 1.
can you also conclude that lambda 2 times lambda is mu?
We could.
If lambda equals 2
We could.
mu. That's helpful.
Does that help me?
Probably not.
I mean, some combination of 1 and 2 is making 1. That doesn't tell me a whole lot. So the question is this already enough to tell me the end of the story?
Probably.
C equals 2x squared.
So you have z on one hand is x squared plus y squared, which becomes 2x squared, as Matthias just said.
And
We
that
also know
equals
that
0.
y squared is x squared.
Wait, but that equals 0. Didn't we say? No.
No. And you also know the linear equation, which said x plus y plus 2z is 2.
X squared.
So you still have this. So knowing that x equals y means you reduce to solving this equation for x. So the z's are equal, these have to be equal.
It's
2x squared plus x minus 1 is 0. So once again, it's sort of boring. We've got a specific x and y is equal to it, and then you solve for what z is. So x, in this case, I'm not going to finish the problem, but x is going to be given by the quadratic formula, minus 1 plus or minus square root of b squared minus 4ac. Ooh, isn't that 9?
For
So then what's the factor?
So you get square root of 9, which is 3. You get minus 1 or 1/2. So that's not so bad. Mm-hmm.
Where did the x vector xy equals c times vector 1, 1 come from in both of those problems? I missed that.
Back. The fact that the scalar multiples add up to 0, which means the vectors have to be parallel.
Oh,
Just looking at the first two coordinates.
Also, where'd you get that second equation from? Z
The
equals-
equation of the plane.
Okay, cool.
So I didn't write it down again, but I still have the same equation of the plane. Okay. Let's do something that's a little more interesting. And then I'll talk about the proof for a smidgen. Find the distance between the line x plus y equals 2 and the ellipse x squared plus 3y squared equals 3. I believe I want to do. So this is a problem we have not yet thought about in any remote form. You've got a line and you've got an ellipse.
can't grab this ellipse.
Something like that.
Something like
And I'm asking you find the distance between them. What does that mean?
Point closest to the line on the ellipse.
So you could imagine taking all points here and all points here and measuring that distance and trying to do what?
Minimize.
Minimize. How do we do that?
It's gonna still be the point where the,
Consider
there's gonna be, yeah, you know what I'm saying.
Consider the
I made myself clear.
the square.
So you could think about this analogous to the way we had Sammy's rock in the lake.
Right.
It's gonna be.
You could imagine moving this line parallel to itself and seeing where it is first
Touching
the ellipse.
Yeah, that's
And
essentially,
that would give you the closest point.
that's what I say. I say do that.
That's what Dan was in essence saying. So you could try to solve this in a similar way, but how would you set this up as a Lagrange multipliers problem? I have two equations, but what am I trying to do? I'm trying to look at distance between a point that satisfies this equation and a point that satisfies that equation.
Oh,
Equal them up.
Well, so I mean, it seems to me I want to point x, y on the ellipse, and I don't want to use x and y for this point.
Why?
So I
Q and
need
zero.
2 other letters,
no.
You.
right? So I have a function of 4 variables, which is, for example, square the distance between these 2 points. Again, I prefer not to do square roots if I don't have to. So I want to look at the function that looks at the square of this distance, subject to the constraints that, no, it's not x plus y equals 2 anymore.
Oh, U plus.
U plus v is 2, and x squared plus 3y squared is 3. There are my 2 constraint equations. Agreed?
Yes.
And now, in this case, Taylor, you might actually be able to see some more geometry to what the lambda and the mu mean, because you're talking about the gradient vector for this equation, the gradient for this, so that's giving you normal vectors, and you're trying to take an appropriate linear combination of the normal that will be pointing in the direction of the gradient of f, which would be in the direction of the vector joining the 2 points. So you might actually be able to rig out the geometric meaning here. So I want gradient of f. I'm going to remove the 2's again. So I want gradient of f is twice what? Well,
X
what's the
minus
partial with
u.
respect to x?
X minus u.
What's the partial with respect to y?
Y minus v.
What's the partial with respect to u?
Negative u plus x.
So you have the negative by the chain rule. And that's supposed to be some multiple of the gradient of g1, which is 0, 0, 1, 1, plus some multiple of the gradient of g2,
0, 0, 2.
which again has a 2 in it, x and 3y. And then, whoops, x, 3y, 0, 0. Okay, this is interesting.
Do we really need the 2 on the left side?
Yes.
Well, officially it's there, but I mean, I'm going to sort of ignore constants anyway, right?
I like that too.
So what is this saying? How is this vector a combination of these?
Well, you could take a look at the easiest case, which is like what lambda is.
Well, do I even need lambda
No.
per se?
Well, you don't, but you can show that like.
But analogous to what we did a few minutes ago, what is it, looking at the fact that you have zeros here, what does it tell you looking at this part of the vectors?
Negative x plus y equals negative y plus 2.
Right, so because you have zeros here, you conclude that x minus u and y minus v are a scalar multiple of 1, 1, which means x minus u equals y minus v.
Right.
That's the statement that must be saying something about
No, isn't it?
having this be tangent if we back it up to the ellipse.
Isn't it negative?
It doesn't make
It is
It's the
negative,
same
but
thing.
It doesn't make a difference.
It still
because-
makes them equal.
Right, yeah.
and what about the other piece, using that this is 0?
Oh, you know that those
It's a
two
scalar multiple of?
1, 3.
No,
X,
X 3y.
x through y.
So we know
X 3y equals.
Okay, so because of the
3y
zeros
equals
here,
x.
we know that this vector is a scalar multiple of that vector. Which in turn, well,
Yeah.
we know that this is a scalar multiple of 1, 1.
So
So
we can,
So x3y has to be parallel to 1, 1.
so x equals 3y.
So x equals 3y. So do you see what that's doing geometrically? That is actually saying that the gradient vector for the ellipse, which is the normal vector, has to be parallel to the gradient vector for the line, which is 1, 1. So you're looking for points on the ellipse where the normal vector is also normal to this guy. That's exactly saying that if we move this line and had it just touch, it would be tangent.
right, sure.
Okay.
So all we really needed to do was take, like,
So we could have done this, you could have done this with high school calculus, you didn't need any of this fancy stuff, but I'm trying to make you understand it, right? So you're getting the point where x equals 3y,
So it's gonna be like. Sure.
and at that point, the normal vector is more or less, if I had done it perfectly to scale, it would be pointing in the direction that's also normal to the line.
Sure.
And similarly, at this point, that would be the farthest away. So at this point, you can plug in and say x is 3y, so 3y squared plus 3y squared is 3. The 3's have it.
Why would that point be the farthest away? Because couldn't you just move like
4.
infinitely down the line?
if you take the distance from
Hmm?
a point to a line, you have to take
Point on the ellipse furthest away from the line.
Oh, okay, yeah.
One
So
fourth.
what do I have? I have
9 and 3 is 12, so y squared equals 1/4.
So you have the 2 points, 3 halves, 1/2 for x and y, and negative 3 halves, and negative 1/2.
I don't think that's
And
gonna.
I'll let you finish the problem, define the corresponding point on the line, and figure out the distance.
I don't think the second one's gonna be the closest one.
I don't think so. Okay. All right, so that should be enough illustration, but I'll actually do the Lagrange multipliers yet again after the exam, when we come back from Thanksgiving, and we'll come back in terms of talking about projections and subspaces, so we will revisit Lagrange multipliers another time. By the way, the exam, which is right after holidays, goes back to close to the beginning of chapter 4,
Right.
right? Section 2 of chapter 4 and runs through what we've just done. So the first 3 sections of, is it 3 sections? 4 sections
Yeah.
of chapter 5 through Lagrange multipliers.
Wow.
So don't forget all your linear algebra.
This actually.
All right, so I want to give you an idea of why Lagrange multipliers works. So there's some cool, so there's a little bit of calculus going on, namely this condition is telling me that I have a manifold near the point. So I'm going to say near A, M can, comma, by the implicit function theorem, which we will do in all its glory next semester, be represented as a graph. say, over the first n minus m coordinate plane. So here you are in Rn. This constraint set looks like some sort of n minus m dimensional thingy that I'm going to assume can be represented as a graph over the n minus m dimensional first coordinates here. So I'm giving basically the last coordinates let's not use x, let's say u. I'm using the first n minus m coordinates and then the last n minus m, last m coordinates. So this is n minus m here. These are the last m coordinates, and I'm saying they're functions of the first. That's what the implicit function theorem is saying. So trust me on that, we'll do a lot more with this in the spring. I want to do the calculus and the linear algebra that we get from this. So I'm assuming that this constraint set, at least locally near A, is a graph over these coordinates. Now, what do I know about f and g with regard to this parameterization that I'm doing here? What do we know?
Well, they,
Well, how is m defined in the first place?
G,
G equals constant. So if I plug in phi of u, what do I get into G? I get a point on m,
Yeah.
and I do G of it. It's constant.
Sure. I was just about to say that.
So as I vary u down here, so let's say u naught is the point that corresponds to A, and as I vary u, G doesn't change when I plug in the points on the graph. What else do I know? What's happening with F?
there's a, it's a critical point of F.
As I move on this surface, this is a critical point relative to all the other points on the surface when I plug in F. So that means u naught is a critical point for the function f composed with capital Phi. What is critical point for a function on a subset of n minus m to m, mapping to m? What does a critical point mean?
Local max.
Well, not necessarily.
But it's like local max within or so.
Critical point.
Derivative equals 0.
Derivative equals 0.
Class. So that's not fog.
What do we know about the derivative of g composed with phi?
It's also constant? Or it's 0? Because
You're
it's
differentiating a
constant.
constant function. What's the derivative of a constant function?
Zippo.
So I have two derivatives that are both 0.
That doesn't mean they're equal.
That doesn't mean they're equal. And in fact, this 0 is a 1 by n minus m 0, and this 0 is a m by n minus m 0. But, all right, so we're almost at the end. You just need a little bit of cool in your algebra here. How do I do the derivative of compositions? Chain rule.
That.
So the chain rule says df at phi of u naught, that's A, times d phi at u naught is the zero matrix, and dg at A times d phi naught, d phi at u naught is the zero matrix. That's sort of interesting. What does it mean if the product of two matrices is zero? This actually came up in your homework.
And one of them is zero?
Doesn't mean that one of them is zero.
Cool.
It's what you didn't say.
So we have this, and we have one more condition that I'm going to put here in the box before I change boards. And rank of dg at A is m.
Are they like orthogonal?
So what does it mean if the product of these two matrices is zero? It does not mean that one of the matrices is zero.
Their row space and column spaces are perpendicular?
Any vector that you get out of the columns of this guy, and you feed it into this guy, it turns into zero. So what does that tell you?
The column.
Column space of the matrix on the right is
Orthogonal.
Is the null,
perpendicular. No.
is the perpendicular to the row space.
Column space of d phi.
Equal.
You feed all those guys into the matrix dg, and you get zero. Right? Any vector that's in the columns here, when you feed it to dg at A, turns into zero. Now you guys were thinking orthogonal. What is the null space of a matrix? Good review for the test.
Orthogonal to the row space.
R prime, or R perp, sorry.
R
Per.
per. Now, let's talk about dimensions.
Talk about three dimensions.
What's the dimension of this null space?
The dimension of the row
What is G?
space.
Yeah, no.
1?
What does this tell you?
Oh, that's
N minus, N minus,
N minus
N.
N.
N minus.
Sure.
Null space is n minus the rank.
Good call.
What's the dimension of this? What's d phi going to have in it? It's going to have an identity matrix and then jump here, right? Because of the, look at the formula for phi.
Yeah.
It's a what by what identity matrix.
And
It's an n minus m by n minus m identity matrix. So what's the rank of this matrix?
N minus N. So they're the same thing.
How can one thing of a certain dimension be a subspace of another thing with the same dimension?
They're
They're
the same.
Thing.
They're
They are the same. Everybody remembered.
Everybody answered that.
What do you got an M? Or like just a squiggle?
All right, we're almost at the end, guys. Hang in there, one more step of reasoning. I haven't yet used this first equation.
That's the problem. Of course.
Oh, just the.
We also have, well, what does the first equation tell me? If I
That
take any of the columns of d phi, what happens when I feed them to df at A? Also zero. So doesn't that mean that the column space of d phi of A
is the null space of DG, DF of A?
is in the null space of df at A?
Yeah.
Sorry, this was you not here. And what's the null space again? It's the perp of the row space. All right, we're almost at the end, guys. Give me one more little bit of energy here.
It's all yours.
What do I get when I put this? Gosh, I can't make stars today. What do I get if I put this together with dagger?
Did you star and dagger?
Star and dagger.
Why didn't you do cloak?
Then,
Well, I'm not good at drawing cloak.
then they're the same.
Now be careful. These are the same.
Sure.
But the dimensions of the multiple.
So that
So
one's also
this
within that
is a
one.
Is
subset
the row space of dg of A perp.
Right.
So the perp of one thing is contained in the perp of another.
Which means the opposite is true, I think.
By your homework
Yeah, I remember this.
that Matthias just said from week 3, I believe it was, or maybe 2, I don't remember.
Probably two. We move pretty quick.
If you have one subspace contained in another, the perps have the reverse containment.
Yeah.
So what do I get if I say the perp of this is contained in the perp of this?
And
Then we
That
go
means the perp of this guy contains row space of dg of A
yes.
perp. Perp contains row space of df of A perp. Perp.
which is the same thing.
This is a sketch.
That's per perp again?
The same.
So this says df at A. The row space of a 1 by Blanc matrix is just the span of that one vector is contained in the span of the rows of dg. Well, that's
Exactly what we have.
that means the vector df of A is in the span of these, which means it's a linear combination of those, and that's the end of the proof. So the linear algebra, the implicit function theorem is used, and then this really cool linear algebra is used using perps and double perps. Have a wonderful break if I don't see you in office hours.